Now, let us looking at interatomic bonds. There are different types of bonds, two classification, primary and secondary. In primary, there are ionic, covalent and metallic bonds, and in secondary, van der Waals and hydrogen bond. Okay, so, we will just very briefly go through these also today. Now, ionic or electrovalent bond, what is happening is transfer of electrons takes place between dissimilar atoms. Okay. Now, you can see here sodium chloride, magnesium oxide or calcium chloride. Okay. So, this example in sodium chloride, so sodium you know there is a +1 possibility, in chloride you have -1. Okay. Now, on the right side you can see the sodium contributes the electron leaving with a closed shell, okay, and that particular electron is taken by the chloride ion, okay, and you have a negative charge on the chloride. So, it is not that they are sharing the electrons, but they are transferring the electrons from one to the other. In case of magnesium oxide, you can see again this one and this one, that is +1 here and +1 here, that is +2, is both are taken by the oxygen here. Okay. So, you get -2. So, taken completely, it is not sharing, it is just transfer. In case of calcium chloride also same thing happens, this is +2 and both are taken by the chloride in 1 and 1, like you can see here 1 and then here 1. Okay. So, just to example to show how the transfer of electrons happen, and these kind of bonds are called ionic bonds. Now, covalent bond here not the transfer, but sharing of electrons is what is happening. Okay. So, example hydrogen, chloride and HCl or hydrochloric acid. So, you can see here you have one for hydrogen and that is being shared here, okay, from each of the atom, it is shared. So, you get that 1s2 as the electron configuration. It is also indicated by this kind of hyphen. Okay. Now, in the second case chloride, you have one here and one here, that is being shared or indicated with this, like this here, okay, or also sometimes by this just a hyphen. Now, in case of HCl also, you have this and this being shared. So, you get that full sharing happening and it is also indicated by this. Okay. Now, covalent bonds, they are directional in nature. Okay. What it means is when you talk about these different type of bonds, there are some kind of angles at which these bonds are placed or angle between the bonds, and they do not change much, they are fixed angles. So, in case of carbon monoxide or CO2, carbon monoxide or CO2, you have 180-degree angle. In case of silica, you have 109, in case of water, you have 104.5. So, these angles have some special nature because of which the other behavior or the rearrangement etc. happens in different material system which contains this kind of atomic structure. Now, you can also see the carbon nanotube, it is all directional, they are not they are very well organized atomic structure. Okay. So, that is what I am saying thereby, meaning that they are directional in nature. Just some examples to show you. Now, just again comparing, we already looked at ionic and covalent bonds. Just to emphasize the difference, in the case of covalent bond, you are sharing the electrons. In the case of ionic bond, you are transferring the electron from one atom to the other. So, you can see here in this case, this is being shared, whereas here both in the right side, both these are taken by the negative ion and leaving a +2 charge for the negative ion and a -2 charge for the positive ion. I mean, sorry, the other way. Yeah. Okay. Now, metallic bond. So, this is mass sharing, means sharing, but in a larger scale of the sharing of electrons among several atoms takes place. We can also look at it as a special case of covalent bond. The octet structure, that 8 electron thing we were talking about earlier, is attained by a generalized donation of valence electrons which form a cloud that permeates through the lattice, and this is why you have a lot of electrons available in the entire lattice structure, and that is why you are able to get the high electrical conductivity also, because you have electrons available which can transfer charge from one point to the other by through conduction. Now, metallic bond is also non-directional in nature. So, you can see what I just mentioned in this picture at the bottom. You have a lot of these red circles which are all the negatively charged or negative electrons, and then this plus sign, the gray color circle, they are all metal atoms. So, electrons and atoms are all everywhere. So, you have a lot of, on the right side picture you can see more, you have a lot of these electrons available around the atoms. Okay, so that is metallic bond. Now, we will talk about secondary bonds. So, until now we were talking about the bonds which are very primary in nature or strong bonds, covalent, metallic and ionic bonds. Now, two secondary bonds we will talk. One is van der Waals forces and then hydrogen bonding. So, what is van der Waals forces? This is generally known as the weak bond. Okay. Now, what is happening, or why such bonds are formed? When atoms come too close. Now, what is this too close? It means in the scale of nanometers. So, very you are talking in the atomic scale, they tend to interact, polarize themselves and attract each other. So, you can see the picture at the bottom where you have a HCl, two HCls, okay, hydrogen chloride or hydrochloric acid. So, you can see HCl. So, this has a very good covalent bond. Here also on the right side same thing, a very good covalent bond. But when these two HCls are coming closer in the scale like in nanometers or so, then there is a possibility of a interaction between them. There is a attraction possibility. Why? Because you have H plus here and Cl is minus here. So, you have plus and minus ions or positive and negative ions coming closer, and then they may form this weak bond. Okay. And even though it is weak, it has influence on the material properties at different states. Okay. Yeah, and these are called van der Waals forces. Now, just a little bit more explanation on this, where you can see here random dipole on one atom and the induced dipole on the adjacent atom. So, look at the left side of the graph. So, here again the distance is written as about 5 nanometer or less. That means we are very, very close. Okay. At that time, on the left side you see random atomic dipole, on the right side you see induced atomic dipole. So, what is happening is it's the same picture. So, on the left side you can see this negative charge is polarized, towards the right side, and the positive charge is polarized towards the left side of this atom, right. Now, what will happen is when this happens, the atom on the right side, that is this one, this gets induced because now you have more negative charge here. So, this will have some influence on attracting all the positive charges to the left side on the right side atom. Now, because of this movement of the positive charge to the left, the electrons will move to the right side on that. Okay, so the negative. So, this is induced dipole. First thing happening on the left side, that is random. Because of that, it induces polarization on the right side atom. So, that is what difference between random and induced atomic dipole. Just wanted to mention this aspect also when we talk about van der Waals bond. And because of this, the material behavior can change a little bit. So, I can talk a little bit about some examples on how these van der Waals forces affect the material behavior. Now, one thing is, when you heat any particular material, what will happen is, first when the heat energy or the heat energy is absorbed by the material, or when the temperature increases, there will be vibrations caused in atomic level, and at that time the first bonds which will be breaking are the weakest bonds, like weak and non-directional bonds will break first, and mostly those are the van der Waals bonds. Okay. Now, while boiling liquid, this is what happens, and also in case of plastics, when you heat the plastic, it starts flowing, the plastic material starts flowing, and then flowing means permanent deformation, and that is happening because of the breakage of these weak bonds. And also mechanical disturbances, let us say you are mixing something, in case of thixotropic materials, they can also lead to breaking of these weak bonds. So, first bond, the type of, among all these covalent or ionic, or in case of metallic bonds or anything, the first type of bonds which break are the weakest bonds, and usually they are the van der Waals forces. So, they have significant influence on surface tension, viscosity, thixotropy, shear thinning, etc. of various materials which we use in construction also. Now, for example, I will just explain this shear thinning behavior here, or thixotropy, you can relate that. So, here you can see the first image where you have some two black things are also going here in between these red circles. So, I can say when this is in equilibrium. Now, when I try to disturb that material, if I try to disturb the material, let us say you take an example of a pudding or something, you try to disturb it, so it starts breaking, right, the material starts breaking. And where do they break? That breaking is happening along these lines. You can see here, these are the two lines in this example where that breaking happens. So, the material starts flowing, it flows easily, or the force required to further flowing the material is to induce further flow of the material is relatively less, and that behavior is what we call shear thinning. I covered this in the previous lecture on materials, the concepts for materials engineering. Okay, so you can look back on that viscoelasticity where we discussed, we talked about what is shear thinning. So, this was something like this, and then you have shear stress, shear rate, and then material behaving like this. Okay. So, here the weakest bonds break first, and that allows the material to flow. Now, hydrogen bond is another secondary bond we are talking, and this has hydrogen has one proton and one neutron, and these are attractions between a positively charged hydrogen, that is here, on one molecule, and a lone pair on a very electronegative atom. Typically, you have nitrogen, oxygen, fluorine or chlorine on another molecule. These are very highly electronegative atoms, because this positive hydrogen gets attracted to this negative atom, and then the hydrogen bond is formed. Example is shown here in this drawing here, where you have example of HF. So, you have hydrogen here, fluorine, and then you have a negative charge forming on this side, and here you have positive charge forming, right. So, because of that, there is this interaction between these two negative and positives, and that is what is hydrogen bond. Similar example, I mean, just to more clarity, you can see here a same example, hydrogen and fluorine, but you have this one here and more negative energy here, more negative, and then because of the hydrogen presence on the left side, you have more positive energy there, and because of this delta minus and delta plus, you have this hydrogen bond forming right here. Okay. Same case in case of this formaldehyde and hydrogen fluoride, you have same plus and minus charge on the facing each other, and which leads to the formation of hydrogen bond. So, these black lines here indicates the hydrogen bond. Okay. Now, look at the picture at the bottom where you have a hydrogen bond and covalent bond shown in case of water. Okay. Now, which is hydrogen bond here? So, you can see for example, this H plus positive charge here and this oxygen has a negative charge on that side. So, this dashed line or the black dotted line we can call as hydrogen bond, and which is the covalent bond, that is this between the hydrogen and the oxygen in the same molecule. Okay. So, within the molecule you have covalent bond, but across two molecules of H2O you have hydrogen bonds. Now, this you know it very well when you have ice formation. Ice actually floats in water. Why it floats? It is all made of same H2O, but there is, because of something, it is floating in water, and then the reason is the density of the ice decreases as ice forms. And why that is happening is coming back to the reason is hydrogen bonds which are formed. You can see in case of water on the left side, in case of liquid water, you have these different bonds, but there is no proper organized fashion. Okay. So, in liquid state, water molecules are closely held together by weak hydrogen bonds. In the right side, when the ice crystals are formed, you have I said ice crystal, right? You have well structured molecule there, okay, or the atomic structure is there, well structured. So, they become stable because of this particular structure, they become stable and arranging the water molecules far apart from each other. You look at the left side picture and the right side picture, left and right. If you look at left, you can see lot more molecules as compared to the one on the right side. So, the density of ice is less. Because of the lower density, it starts floating in water. You cannot really push ice into the water. It's very difficult. It is not possible because of this atomic structure. And also because of these type of bonds present, it also asks for high boiling point, surface tension, etc. Because you need, when you say high boiling point, means you need more energy to break these bonds first. So, that is also adding to the high boiling point. So, these kind of bonds definitely affect the mechanical and other properties of the materials. Now, presence of hydrogen bonds also can enhance the mechanical performance and heat resistance of some polymers. Here is an example of nylon and Kevlar. Kevlar is very it is used for bulletproof material. It is actually a bulletproof material developed for that purpose only. Now, you can see here where is the hydrogen bond here. This is one, this is one, this is one between oxygen and hydrogen there. Here also you can see like that, okay, connecting these different chains. So, you can see this is one chain, this is another chain, and then there are hydrogen bonds between the chains. They really help in changing the behavior or in enhancing the behavior of these materials. Now, we covered these different type of bonds, and these type of bonds can be used to classify, or different materials can be classified based on the type of bonds which are present. For example, if we are talking about metallic materials, steel or metallic bonds, steel, iron, aluminum, etc., they have metallic bonds. And in case of cement, concrete, brick, glass, aggregates, they are all typically ceramic materials, and they will have other type of bonds, not really the covalent bond or ionic bonds, etc. And other organic solids, you have asphalt, plastic, wood, they also have different. So, these materials have different set of they can be classified based on the type of bonds which are present, and then the behavior is also very different. So, in future lectures, we are going to first look at how the metallic materials behave, and then looking at their microstructure with different type of defects in the metallic materials, and then we will look at inorganic and organic, inorganic and non-metallic materials, and then finally we will also look at how the organic solids or organic materials behave. I think for today we are going to close. To summarize, we looked at atomic structure, we looked at electron configuration. It is very important to recap some of those knowledge which you already have, and then we looked at Condon-Morse diagram, how it can be used to relate to the mechanical behavior like elastic modulus or tensile strength, etc. And then different type of bonds also we discussed, and also material classification based on chemical bonds which we will talk in more detail in the coming lectures. I think with that we will close this lecture. Thank you.